So my talk is about Full HD super multiview display with a deep viewing zone. I'm Hideki Kakeya from the University of Tsukuba. So this is the table of contents of my talk. I'm going to first talk about the background of this research, and I'll just give a brief review of my previous work, and then I give just explanation of our proposed method, and we show the experiments and give the conclusion. First, the background. So most of the people here know what vergence accommodation is. But just I give a brief explanation on this. So when we are doing things in the real world, when, for example, if the viewer is looking at this object, the vergence, the binocular divergence is converged to this point, while the accommodation, focal accommodation of the crystalline lens is also focused on this object. But when we show an image with the conventional stereoscopic display, the left eye image is shown here, and the right eye image is shown here, and with the kind of artificial parallax, the right eye is looking at this direction, the left eye is looking at this direction. So the vergence is reproduced while the light is coming from this screen, so the eye's focal accommodation should be fixed on the screen to just see the object clearly in the retina. So this vergence, the distance given by the vergence and the distance given by accommodation contradicts with each other. So that's the problem of the conventional stereoscopic displays. So to solve this problem, there have been several research on super multiview displays. So how it works is that, so this is the pupil of the eyes, and if we can just show more than two light rays to each eye, for example, if this image is observed from here, and this image is observed from here, we can just stimulate focal accommodation of the eyes. Then, and if we do the same thing for the left eye and the right eye, then we can just reproduce not only the vergence, binocular vergence, but also the focal accommodation, so that we can realize natural 3D imaging. But the problem is that we have to prepare so many views to realize this kind of super multiview displays. So one method to reduce the number of views for super multiview display is to combine with the head tracking system, where the light rays for the left eye and the right eye are generated only around the eyes. For example, so this is the work by Professor Takaki. He is also a kind of great contributor to this conference. And he just realized this system in 2011. So the 4 views are generated around the right eye, and the 4 views are generated around the left eye. Then if the viewer moves, we can just move the image here. Then we can keep on showing super multiview images for the left eye and the right eye. But in this system, they use a lenticular lens sheet. So the resolution drops into just 1/8 of the panel here. So it still suffers from some just resolution loss because it's special multiplexing based system. So to solve this problem, we've made a Full HD super multiview display based on time division multiplexing, not special multiplexing. So we used Full HD panel, and we generated 9 views for each eye. So we generated 18 views in total. How we do that is we apply sextuplexing parallax barrier, time division parallax barrier. So, and we also 180 Hertz refresh rate. Then we can attain 30 interlace frame per second. And with this, with only this sextuplexing time division, we can just generate 6 views. And to multiply the number of views, we use, so this is the point, we use 2 panels with opposite color filter alignment. And then we can just, assign different angles of rays for each color. Then we can generate 18 views in total. So how we do that will be explained in detail with this figure. So it's because it's time multiplex, so this is the first frame of the 6 frames. So in the first frame, we just, so just the slit is, 1/6 of the slit is bright in each frame. And so the order here, note that the order of the color filter is different. So this slit pattern is blue, green, and red, while the imaging panel in front is, the order is red, green, blue. So the order of color filter is opposite. Then, so the light rays and the green rays and blue rays are directed into slightly different angles. In this way, we can generate 18 directional light here. So this is the first frame. Then in the next frame, we show an image like this. So here, this slit is bright, and we can generate 18 light rays again. So in the next frame, we just show image like this, next, and next, and next. So after 6 frames, all the pixels in the back are bright at one time. So the full resolution image is reproduced after 6 frames. And we can generate 18 directional light with the full resolution of the display panel. So that's how it works. So actually, we presented this, we just gave a presentation of this work on SID this year. And this is the prototype of the system. This is how the prototype system is kind of made. So the interval between the front panel and the back panel for slit is 30 millimeters. And the viewing zone for each pixel is calculated with a very basic geometry, the similarity of triangles. So the viewing zone, actually it's magnified, but actually it's much smaller. But just to show the triangle, we are making a little bit bigger triangle. So the pixel pitch is 0.092 millimeter. It's a subpixel pitch. The width of subpixel is 0.092 in our display panel of the prototype system. So this is the distance between the panels. And if the viewer is 750 millimeters away from the front panel, the width of each viewing zone is 2.3 millimeters. So actually, the aperture of the pupil is around 4 or 5 millimeters. So this small width of viewing zone can reproduce can just stimulate focal accommodation. So it's like this. So the width, as I said, the width of the viewing zone is about 2.3 millimeters. So, and we can show nine views for each eye. So the width of the left eye viewing zone is 20.7 millimeters. And so left, right, and left, right. And here, the right eye viewpoint is generated around the right eye. And so in this way, we can show more than 2 light rays to each pupil of the eyes. So this is the picture taken with the camera. So we show 2 cones. One is 100 millimeters in front of the panel, and the other is 100 millimeters behind the panel. And when the camera is in focus of the front cone, the back cone is blurred, while the focus is in the back cone, the front cone is blurred. In this way, the kind of focal depth is reproduced in this system. And this is actually we're showing a kind of natural image. So this is the standard stereoscopic image. So both the front part and the back scenery are both in focus, while with the super-multiview display, when the focus of the camera is in front, it's clear and the scene is blurred. While we focus on the back part, the front part is blurred. So in this way, natural focal effect is reproduced in this system. So we're going to the original work presented here. So the problem of this system we presented at the SID this year is the viewing zone in the depth direction is quite limited. So because, as I said, the viewing width of the viewing zone for each eye is about 20 millimeters. It's not that wide. So when the viewers go in front or into the back, actually the eye can easily go out of the viewing zone. So we want to adaptively change the width of the viewing zone for the left eye and the right eye when the viewer moves backward and forward. To do that, we apply adaptive type division. So in the original system, we just applied sextuplexing time division. And if we just change the number of time division, the width of the viewing zone can be changed. So I'm going to explain why it can be achieved. So this is so when the viewer is close here, so it's a triangle again here. So it's based on the similarity of a triangle. So this is the case where I explained in the previous slide. So when the viewers go farther, then the viewing zone for each subpixel becomes wider. So it's a quite simple geometry. So when we applied time division sextuplexing, actually this is the same figure we showed previously. And when we apply time division quintuplexing, then so here when the viewer is farther from the screen, the viewing zone for each view is wider. Then when we apply quintuplexing, the viewing zone for each eye is almost the same. Actually, so it's actually with quintuplexing, the number of viewing zone is 15. It's 3 times 5. So the viewing zone the width of the viewing zone for the left eye and the right eye is not the same. So it's a little bit unbalanced, but still we can secure the same viewing zone for the left eye and the right eye. The average depth is the same. And when the viewer goes farther again, then we apply quadruplexing. So here, when the viewer is farther, then the width of each viewing zone becomes wider again. Then if we just decrease the number of views for the left eye and the right eye by applying quadruplexing, then the same width of the viewing zone is secured for the left eye and the right eye. In this way, we can just keep on showing a stereoscopic image when the viewer moves forward and backward. And here the width of the viewing zone is 3.45 millimeters. So it still can, in this situation, we can still just impinge more than 2 light rays for each pupil. So this is the experiment. So this is the hardware I just made, and we're going to give a demonstration on this system in tomorrow's demo session. So here we can show the image like, so we show the white image to the left eye and the black image to the right eye. And in the sextuplexing, it works when the viewer is 750 millimeters away. And here, when the viewer is 900 millimeters away, then quintuplexing is the best. While the viewer goes farther, then quadruplexing is the best. So we can show two different images to the left and the right eye by just applying adaptive time division multiplexing. So we're going to go give the conclusion of the talk. So we have expanded the viewing zone of a Full HD super-multiview display in the depth direction by applying adaptive time division multiplex parallax barrier. So we've confirmed it works with the prototype system. So that's all for my talk. Thank you very much.